Okay, can you see it? Yeah. So I thank the organizers for the opportunity to talk here, and my talk is about notes and grades. That I choose it because the grade technique I need uses some algorithmic relations for grades, some things related to normal forms and grades, but in fact the main result is without any mentioning of these things, and in fact it's really far from growth and rises. Sorry. But I have a pair of funny pictures, and I hope that you like it. So the definitions I need is just the standard definition of nodes and links. A link, just a compact one-dimensional smooth submanifold in a three-dimensional sphere or in a three-dimensional space, and a node is just a one-component link. And we consider these guys up to equivalence up to ambient isotopes. So if something can be moved to another link or not, we consider them as one and the same thing. So the set of nodes, when we see them like this, is just some countable set. And the main aim of this research is to understand the structure of this countable set, because in this just definition we can't see any relations between distinct nodes and so on, but if we manage to find some special ways to see nodes and links with some relations, we can find some structure. And a classical approach to see the structure in this space of nodes uses braid groups. So the braid group is just the definition of braid definition. It's a very famous group, and we can use these groups to see a structure on the set of nodes, because when we present our grades in their geometric interpretation, here we see, if we take our group with this set of generators as above, and for each generator we associate such a picture like low left. This is the first picture, is for generator sigma I. The next picture is the diagram for generator sigma I inverse, and so on. And then when we take any element of our braid group and present this element as words in these generators, we have a possibility to form a diagram from this word in generators like this. And then, if we add strings to the ends of this diagram, we obtain a picture that can be interpreted as a projection of a link or a node if we have only one component of it. And this is the Alexander's theorem that for any link and any node in space, we can find a braid group, some number of strings, and a braid in it, such that under this representation, this braid will represent exactly our link chosen. So we obtain a map from the union of braid groups, purely algebraic structure, to the set of nodes and links, and the Alexander theorem says that this map is surjective. So we see some algebraic structure in this complex set of except this way to see such structures in the nodes and in the set of nodes. Of course, there are many other interesting things, but all these ways to see some structure are rather complex. And there are several representations in terms of braids, and all these representations are aimed to see something subjective. And in fact, it turns out that in some cases it is more interesting to construct an injective presentation to embed sets of braids inside the set of all nodes. It will help to count the number of nodes with respect to some vectors. And the main result I want to present now is the following thing. Please see this picture. Here we see just some node template. Yeah? This is just a projection of some node on this slot with red rectangle. Is just imagine that at first we have just several vertical strings there. Then this picture will be just a picture of some node in space. This is an example with 5 strings, but we can do the same with any number of strings. And the sense of this example is as follows. If we take any two distinct pure braids, this pure braids is when the strings of our braid goes from the first point upwards to the first point down, from the second point upwards to the second point down. It's just in order to obtain a node and not just a link with many generators.
And if we take two distinct pure braids and insert them in this red rectangle on the left, then we always from distinct braids will obtain distinct nodes. So this is unusual result for the set of nodes because it's a hard, difficult algorithmic problem to distinguish whether a given diagram of a node represent a non-trivial node or just something trivial, whether two given diagrams of nodes represent equivalent nodes or not equivalent ones. So this is quite an unusual thing that we can take a group of braids and just with the help of this template embed all the group into the set of nodes. Oh, sorry, I have a call from Nikolai Nikolaevich. Алло? Алло, Николай Николаевич. Слышно?
It was a wrong call. It was a missed call. Yeah.
Okay. So back to the picture. So we have a very unusual picture here. The theorem states that if we have two distinct braids, we will obtain, inserting these braids in this red rectangle on the left, we will obtain distinct nodes. So these provide us with a mechanism of embedding algebraic groups in the set of nodes such that distinct elements go to distinct elements in the set of nodes. And you see, this is similar to that picture of Alexander theorem. In Alexander theorem, we just close the strings directly. And in this template, we just close the strings with some additional knotting. On the picture, you can see the structure is as follows. We have a main large knot, a trefoil here. So all our strings first entangle in some large knot. And then we take two first and second string and entangle them in a little knot of tangle of two strings. Then we take the second and the third string and entangle them again. Then we free the first and second, take only third and fourth strings and entangle them again. So to obtain some in many places locally entangled knot. And then we can guarantee that the result we'll obtain will give us something that embed the elements of braid groups into the set of nodes. On this picture, this small red square is just to show that in this place, the strings are not trivially, flow not trivially, but a twist is added to obtain exactly the some knot and not a link with several components. And from this template, we obtain the main corollary, which was the main point why we construct this embedding. So the result is that the number of nodes with a given arc index grows faster than any exponential function. Arc index for a given node is just the minimal number of vertical lines in any diagram like this one for a given node. And so I think that it will be enough for my talk, because really the main thing is this picture, and here it is, you can see it. So thank you very much for your attention.